Hello, I am Channa Bankapur. I'm going to discuss my solution to the LeetCode problems binary tree tilt and two sum less than k. Both of these problems are daily challenges for today in LeetCode. So I'll start with the first problem, binary tree tilt. It's a non-premium daily challenge problem. So we have a binary tree here, and we need to find the sum of every node's tilt. So a tilt of a node is defined as the absolute difference between the sum of sum of the values of all left subtree nodes and some of the values of all the right subtree nodes. So the difference is going to be the tilt, and we need to find tilts of every node and add them, and that sum is the result we are expected to return. So let me clarify that with an example. So the first example is too simple. The second one is actually much better. Let's start with that. So we have a tree here, which is given on the left side. And so if you look at the tilts of each of these nodes, so tilt of the leaf nodes are always going to be zero because they don't have left and right subtree. That's why we have tilts here. On the right side, we have tilts of every node noted here. And what about the tilt of this node? So the tilt of this node is there is a left subtree which has some whose sum is 3, and right subtree sum is 5. 5 minus 3 is going to be 2. That's why the answer is 2 in this case, or the tilt of that node is 2. And the tilt of the node which has 9 here, a value 9, there is no left subtree, there is only right subtree. In that case, the tilt is going to be the value of that one of the subtrees we have. So in this case, it is 7. And for the root, we need to find the sum of all the nodes of the left subtree, which is 10 in this case, and sum of the values of the right subtree is 16. So 16 minus 10 is 6, and that is the tilt of the node. And we need to find sum of all the tilts, which is 6 plus 2 plus 7, that is 15. That's why 15 is the answer here. All right, so that's what we need to find. And a brute force approach could be, find the sum of the values of all the nodes in the left subtree and right subtree and find the difference, and that's going to be tilt of a node, and do it for all the nodes, and we're going to get the answer, which is very inefficient because there is a clear redundancy in terms of finding the sum of the element, some of the values, as in some of the values of the nodes of a subtree, because when you do it for the subtree of a subtree, that is going to be reused, that can be reused when you find the sum of the values of a subtree. So let me explain that with this example itself. The way I want to do it is, we can find the sum of all the values in a subtree, and along with we can find the tilt of that node and the sum of the tilts of all the subtrees, and that way the root can actually use in one shot. Okay, let me elaborate that example. So I have something like this here. So I'm going to consider even the null nodes here, which are these 7 possible null nodes. So what I'm going to do is, so I'll start with the top and then go recursively. So when I reach a null, that means in this case there is no node. So the sum of the nodes is going to be, some of the values of the nodes is going to be 0, and tilt obviously is going to be 0. So actually there is no node, so there is no tilt defined, but let me still call it as 0 comma 0. But for the node, this is actually a leaf node, and the sum is going to be 3 because that the node's value itself is going to be the sum, and tilt in this case is going to be 0. And that is also clear because if you know the this 0 and this 0, this difference is going to be 0, right? And similarly we are going to get 0 comma 0 here, 0 comma 0 here, and this is going to be 5 comma 0. So 5 is the sum, and 0 is the tilt. Now for this node, we are going to get because of 3 plus 5 plus 2 is going to be yeah, 10 is the sum, and tilt is going to be difference between 3 and 5, which is 2, right? So this 10 comma 2 indicates 10 being the sum of values of all the nodes in the subtree, and 2 is the tilt is the difference between the sum of the left subtree and sum of the right subtree, right? So now if I go on the right side, so we're going to have again 0 comma 0 here, 0 comma 0 for all the null values. This is more like a base case stores, and we're going to have 7 comma 0 here. And in this case, now look at this, sum is going to be 7 plus 6 16, and tilt is going to be difference, which is 0 and 7. So this 0 and 7, that difference is going to be 7. Now, what about the root here? So for the root, we are going to get this sum. Sum is actually not useful, but well, let's do it. 10 plus 16 plus 4 is going to be 30, right? But the tilt is going to be this 10 plus 16. Sorry, difference of 10 and 16 is going to be 6. But it's that is the tilt of the current node, but we want the tilt of the whole tree itself, right? So which is going to be these 2 and this 7. So the tilt is going to be 2 plus 7 plus 16 minus 10, which is the current tilt. So that's how the whole thing I'm going to return is going to be, or actually for the root node is going to be 30 comma 2 plus 7 plus 6 is going to be 15, right? And 15 is the tilt value here, as in it's the sum of the all tilt values of all the nodes, and that is what I'm going to return, right? So if you see here, this is a simple recursive way of doing it, as in a DFS way of doing it, and it can be done in linear time, right? So let me show you my code. It's not too difficult to understand. So I have a helper function called f, and so f is going to basically find both some of all the nodes in that subtree in that tree, and also the tilt, or actually some of the tilts of all the nodes in the tree, right? So which is a pair. So that's why the second one is going to be the sum, tilt sum. I'm going to return that. And if you look at here, this is the base case I was mentioning. If the node is a null pointer, then I'm just returning 0 comma 0. Otherwise, I'll solve for the left subtree, right? So we are going to get it as left. It's a pair, and similarly we'll solve it for right subtree. And node sum is the sum of values of all the nodes in the tree, which is whatever we get it from left and right, and then the current value of the current root, right? So all of these three put together is going to be the sum, right? And what about the tilt sum? It is the current tilt, which is going to be the absolute difference between the sum of the node values of left and right, which is the first value in the pairs, and the the sum of the tilt values of all the nodes in the left subtree and all the nodes in the right subtree. That also I'm going to add, because I'm going to get the tilt sum overall. It is not just tilt of the current node; it is tilt of some of the tilts of all the nodes in in the tree. So that's how I'm going to return node sum and then tilt sum. Finally, tilt sum is going to be useful. I'll return that, right? So if this is very clear, as in it's very clear that it's going to work in linear time. It's a simple recursive one. So let me submit that and make sure it works. It is accepting, and it should work pretty fast. All right. So let me quickly go to the second problem, which is a premium problem to some less than k. It's a standard problem. There is a standard problem of finding sum of two elements in an array which is equal to some value like k. But in this case, we want to optimize. We want to find the sum which is less than or equal to k, but whatever that is actually max, right? Instead of just maximizing it, we are actually putting a constant here which should not be greater than or equal to k. So yeah, let me define the problem again. So given an array of elements, we need to find two elements, a pair, whose sum is less than k, but we want to maximize that. So that's an optimization problem. So if you take an example here, actually let me explain the solution directly. So a pre-sorting method with two-pointer approach is actually very useful here. So I'll start with a sorted version of this, so which is going to be one. So we have how many eight elements here. So the first element is 1, and second is 8. Third is going to be 23, 24, 33, 34, and 54 and 75, right? So we need to find a pair of elements whose sum is actually not more than or actually lesser than 60, right? K equal to 60 in this case. A two-pointer approach for this one is going to be, the first pointer is going to be the smallest one, and first pointer is going to point to smallest, and second the other one is going to point to the last. So the sum of this is 76, which is not following the, as in which doesn't satisfy the constraint. So we're going to skip that. If you skip it, the next one needs to be lesser than this, right? The sum has to be lesser. So incrementing the low pointer is not going to be useful. It will only increase the sum value. But if you decrease the high pointer, the value is going to decrease, and we are expected, or we are actually trying to get to less than 60. So 1 plus 55 is 1 plus 54 is 55, and that is a acceptable thing. So for my the result is going to be 55 now. Maybe initially I'm going to start with -1, because if we don't find anything, -1 should be returned. So now 55 is better than -1, so I'm going to discard -1 and then go to 55. Now, now I'm being greedy, and then I want to increase this 55, right, as much as possible, maybe up to 59 also. So I'll increment the low pointer here, because if I decrement the high pointer, it's going to reduce the value. If I increment the low pointer, it's going to increase the value. So I'll try to increase the value now. And 8 plus 54 is 62, which it crossed the limit. So it's not something we can consider. Now again, we want to decrease. So we'll decrement the high pointer. So 34 plus 8 is 42. 42 is acceptable. It is within the limit, but 42 is not better than 55. So that's why I'm going to discard it right away. I'm not even going to consider that. So 55 is the best sum found so far. What do we have now? 42. So 42 is lesser, so we want to try to increase. So if I increment the low pointer, now 23 plus 34 is going to be 57. 57 is better than 55, and it is acceptable. It satisfies the constraint, so I'm going to consider that. So now the best sum which satisfies the constraint is 57 so far. We are being greedy. We'll try to increment the low pointer. So went to 24. Now 24 plus 34 is going to be 58, which is even better. So we got a better sum. And again, we being greedy, we increment this low pointer 33. So 33 plus 34 is going to be 67, which doesn't satisfy the constraint. So now it's time to decrement the high pointer. We come down here. In this case, low and high pointer both are pointing to the same thing. That means they are not two different numbers, right? So we should not be adding them, right? So I'm gonna stop now, because we don't have any more pairs we can consider. And that's out. 58 is the answer. So this is the method, which is both pre-sorting, because we sorted in the beginning, that made things simpler, and also we are using two-pointer technique, right? So two-pointer technique is a greedy way of reducing the range. So we are trying to find an optimal range here, but instead of considering a lot of ranges, which are actually, there are big of n squared possible ranges, but two-pointer approach is being greedy in the sense that it only considers big of n possible ranges and then finds the optimal among them, right? So that's why this works in linear time. All right. So let's see. The code is obviously again going to be very simple knowing this idea. So I'm going to sort in the beginning, that is the pre-sorting idea. And then the low and high pointers are going to be 0 and n minus 1. And max sum is initialized to -1, as we discussed. And as long as low is less than high, that means if low becomes high, obviously we don't have a pair. So as long as we have a pair, I'm going to consider this one. So if the sum is less than k, it is the constant satisfies. In that case, I'm going to see whether I got a better answer, right? So keep track of the best. And yeah, in that case, I'm going to be greedy, so keep incrementing it. Keep incrementing the low pointer. If this does not satisfy the constant, that means we need to decrease the sum. So we're going to decrement the high pointer, and that keeps on going. So in every iteration, either we increment the low pointer and decrement the high pointer, and that's how in linear time both low and high are going to meet, right? So finally, we have an answer here. All right. So that's it should accept. Let me submit again and make sure. So it accepts, and then this should work really fast. All right. So I hope these solutions are easy for you to even understand, and you must have already implemented. If you implemented in any different ways, let me know. Otherwise, please like the video and subscribe to the channel, and keep coding every day. Thanks for watching.